Welcome to The Explainer. Every single time you save a file or maybe send a text, you are using magnetism. It's everywhere. But where does that invisible force, where does it actually come from? Well, the answer is kind of surprising, and it all starts with something really simple: moving electricity. So today, let's trace that connection. Take a look at this hard drive. Almost all of our modern tech relies on magnetism, just like this. And the secret here? It's not some big permanent magnet tucked inside. No, it's a fundamental principle of physics. It turns out that moving electric charges, what we call an electric current, they generate their own magnetic fields. And that link, right there, between electricity and magnetism, that's the magic that makes our entire digital world possible.
Okay, so we've established that a current creates a magnetic field. Simple enough, right? But how strong is it, and what shape does it even take? If you have a current flowing through, I don't know, a straight wire or a circle or just some random squiggle, how in the world can we figure out the magnetic field it creates at any point in space? That is the puzzle we are going to solve today.
So to answer a question like that, you're going to need a pretty powerful tool. And in physics, our tools are laws. This one is named after the two scientists who figured this whole thing out. So let's get into it. Welcome to the Biot-Savart law.
Okay, so here's the really clever part about this law. Instead of trying to calculate the field from the entire wire all at once, which, trust me, is super complicated, Biot-Savart breaks the problem down into tiny, manageable pieces. It gives us a recipe to find the little bit of magnetic field, what we call dB, that comes from just one tiny infinitesimal segment of the wire, dl. And the whole idea is, if you can figure it out for one little piece, you can just do that for every single piece and then add them all up. It's like building with Legos to get the final shape. So, to put it a bit more formally, the Biot-Savart law is what we call an empirical law. And all that means is that it's based on actual experiments and observations, not just pure theory. It's a proven recipe that lets us calculate the magnetic field from pretty much any electric current. You just add up all the little contributions from every single tiny piece of the wire, and boom, you've got the total field at the exact spot you care about. And here it is, the law in all its mathematical glory. Now, I know, it looks a little intimidating, but don't worry about the symbols too much. It's really just packaging everything we've been talking about. You've got I for the current, dl for that tiny piece of wire, r is the distance, that mu0, we call it mu naught, that's just a constant of nature, a number that makes the units work out. But the really important part, the key to the whole thing, is that little x. That's a cross product, and it's a bit of math that tells us something absolutely crucial. The direction of the magnetic field is always perpendicular to both the wire segment and the line pointing to it. That's the reason the field wraps around the wire.
Okay, we have our tool. Let's get our hands dirty and actually put it to work. And we're going to start with the simplest case we can think of: a really long, straight wire with a current running through it. So, picture this, an infinitely long, straight wire. It's carrying a current, we'll call it I. And our job is to find the magnetic field at some point, let's call it P, that's a distance r away from the wire. Now, using the Biot-Savart law means we have to do that whole process we just talked about. We have to add up the effects of every single tiny piece, dl, all the way up and down the wire. Now, this is where a whole bunch of calculus would normally happen, but I'm going to spare you the details. Trust me on this one. After you do all of that math, something pretty amazing happens. That really complicated-looking law, it boils down to this beautifully simple result. The magnetic field B is just our constant, mu naught, times the current I, all divided by 2 pi r. That's it. It tells us the field gets stronger with more current and weaker the farther away you get. So simple, so elegant. And this is what that beautiful equation looks like in the real world. The magnetic field lines actually form these perfect concentric circles all around the wire. Look at how the little compass needles all line up, pointing around the circle. Or how these iron filings arrange themselves into those perfect rings. And notice how the rings get more spread out as you go further away? That's the field getting weaker, exactly what our equation told us would happen.
So, we know the field is made of circles, but which way are they spinning, clockwise or counterclockwise? Well, for that, there is an awesome little trick called the right hand rule, and you can do this right now. Take your right hand, point your thumb in the direction the current is flowing, and look at how your fingers naturally curl. That direction? That's the direction of the magnetic field. It's a super useful trick for getting a feel for these invisible fields.
All right, so a straight wire was pretty straightforward, right? But the beauty of the Biot-Savart law is that it should work for any shape.
So let's up the ante a little bit. What happens if we take that wire and bend it into a loop?
Okay, so now we have a circular loop of current, and we want to figure out the magnetic field right down the middle, along its central axis. And here's where we get a little help from something beautiful: symmetry. Think about it. For any little piece of current on one side of the loop, there's a perfectly matched piece on the opposite side. And it turns out all their magnetic field components that point sideways, they just cancel each other out perfectly, all the way around the loop.
So what's left? The only bits of the field that survive are the ones pointing straight down the axis. And when you add all of those up, you get another wonderfully clean result. Right at the exact center of that loop, the field is just mu naught times the current divided by twice the radius. And hey, notice anything? The pi is gone. It's a different geometry, so we get a slightly different and even simpler formula.
And now, for the big reveal. Just look at the shape of those field lines coming from the current loop. Does that pattern look familiar at all? It absolutely should. It is identical to the field from a simple bar magnet. And this is no coincidence, folks. This loop of current is a magnet. We call it a magnetic dipole. This is a huge insight. It's telling us that on a fundamental level, all magnetism, even in a permanent magnet, comes from tiny circulating currents.
Okay, let's just take this one step further. We know a wire with a current creates a magnetic field. We also know that magnetic fields push and pull on moving charges, right? So, what do you think happens when you put two current-carrying wires next to each other?
Well, it's really a two-step dance. First, wire number 1 creates its own circular magnetic field, just like we saw. Now, wire number 2, with all its own moving charges, is just sitting there, inside wire 1's magnetic field. And since we know fields exert a force on currents, that means wire 1 has to be either pushing or pulling on wire 2. And of course, Newton's third law tells us it's a two-way street. Wire 2 is doing the exact same thing right back to wire 1.
And what happens is, once again, surprisingly simple. If the currents in the wires are flowing in the same direction, we call that parallel, the wires actually pull towards each other, they attract. And if the currents are flowing in opposite directions, anti-parallel, they push each other away, they repel. It's this unseen magnetic force, all based just on which way the current is going. And you guessed it, we can put a number on this. There's an equation for the force on each little bit of wire. And basically, it just says that the force depends on the current in both wires, I1 and I2, and it gets weaker the farther apart they are. So more current, or putting the wires closer together, you're going to get a stronger force. Now you might be thinking, okay, that's a neat little side effect, but this force between wires, it's not just some cool party trick. It's so unbelievably precise and fundamental that we actually use it to define one of the most basic units of measurement in all of science. And that unit is the ampere, the amp. And this right here, this is its official, honest-to-goodness definition. An ampere isn't defined by, like, counting how many electrons go by. Nope. It's defined by the force we've been talking about. If you set up two long wires exactly 1 meter apart in a vacuum, and you run a current through both that produces a force of exactly 2 × 10⁻⁷ newtons for every meter of length, then that current, by definition, is 1 amp. So think about where we ended up. We started with a simple question about where magnetic fields come from. And we found that this invisible field, created by a tiny piece of current, adds up to produce a force so precise that we literally use it to define how we measure current itself, the ampere. It all comes straight from the Biot-Savart law. And it leaves us with a pretty cool thought to chew on. Since parallel currents attract, what do you think is happening inside a bolt of lightning, where all that immense current is flowing together? It's actually pinching itself inward. Thanks for joining me on this explainer.